So here we want to find the area between the sine graph and the cosine graph over the interval between 0 and pi. Now let's remember what those graphs look like. Sine starts at 0, goes to pi over 2 at 90, it goes up to 1. Then it comes back to 0 at pi. At negative 1, it's at 3 pi over 2. And then it comes back to 0 at 2 pi. So remember, the sine starts at 0, goes up, then down. Now the cosine is weird because it is has this y-axis symmetry like it does. It starts at 1. You'll see a half of a bump. Then it goes down to negative 1, back up, and up to 1. So these points here that's pi over 2, and that's 3 pi over 2. So the area between the curves, this is what's interesting. So this point here, they are equal at pi over 4 because we know both the sine and the cosine touch each other, or the same values at square root of 2 over 2. That's where it's 45 degrees, or pi over 4. So this is pi over 2. This is 3 pi over 2. No, it's not. That's 3/4. 3 pi over 4. Sorry. And then pi, and then 4s, and then 3 pi over 2. And then 2 pi. Okay. Now they only want us to go from 0 to pi. So for the first portion of things, the cosine graph is on top until they meet up at pi over 4. And then the sine is on top the rest of the way until we hit a value of pi. Okay? So that's really important when we go to set up our integral. So from 0 to pi over 4, our cosine is on top. So that would be cosine minus sine. But from pi over 4 till the rest of the way, till we hit the pi, because that's where they told us to stop, the sine is on top. So it's very important that you set up your integral in the right boundaries. If you don't set up the right boundaries, it isn't going to work properly. So how do we take the antiderivative of each of those? Well, remember, the derivative of a sine is a cosine. So a cosine goes perfectly backwards to match a sine. The derivative of a cosine is negative sine, so we need a negative sign to go backwards perfectly to match a cosine. That being said, the antiderivative of that is a sine. The antiderivative of that, since it has the negative on the page, is a cosine. Okay. The antiderivative of a sine needs a negative there, so that's going to be a negative cosine. The antiderivative of a negative cosine, because it goes back to a sine, and whatever is on the sine would be on that, we keep that. Let's make some more parentheses there to help us. So let's remember our points on the unit circle. At 0, the sine is 0 and the cosine is 1. At pi over 4, the sine and cosine are both square root of 2 over 2. At pi, the cosine is negative 1 and the sine is 0. Okay, that being said, so we're going to put pi over 4 into both of them. So that would be square root of 2 over 2 plus square root of 2 over 2. Now we're going to take the sine and cosine of 0 and we're going to subtract that. Well, the sine of 0 is 0, but the cosine of 0 is 1. Okay. Now let's do this next one. If I plug in our upper bounds of pi, I get the opposite of the cosine at pi. The opposite of the negative 1 would be a positive 1. It doesn't look very good. Let's make that look a little better. Then we get the opposite of the sine at pi, which is 0. The opposite of 0 is still 0. Now we're going to subtract when we plug in the lower bounds. So that's going to be the opposite of the cosine of pi over 4, which is negative square root of 2 over 2. And then the opposite of the sine at pi over 4, another negative. We'll subtract square root of 2 over 2. Okay, so let's bring everything together. So we got square root of 2 over 2 plus square root of 2 over 2 minus 1 plus 1 plus square root of 2 over 2 plus square root of 2 over 2. Now, the plus 1 and the minus 1 are going to cancel out. So that's going to cancel out. Look at how many square root of 2 over 2's we have. We have 1, 2, 3, 4. So we have 4 square root of 2 over 2's. These are both just the number 4 and 2. 2 goes into 4 2 times. So we have 2 square root of 2 is the area between the curves from 0 to pi. So that's that one. So that's kind of a neat one. So there's example 6.3. Let's look at example 6.4. Now 6.4, they have drawn it for us. They want us to calculate the area that is shown in the region R. Okay? So let's kind of zoom in a little bit. And let's look at that region. So there's kind of this separation right here. So let's account for that. This is just the area under x squared from 0 to 1. We know how to write that. The area from 0 to 1 under x squared is the integral of 0 to 1 of x squared. Okay? Now, this one, this side from here over, it is just the area underneath that linear equation they gave us. So it is from 1 to 2, it's just the area under 2 minus x. That does say 2 minus x. That is beautiful. Okay. So what's interesting about that area is that area, it's not the area between the curves. It's the area of one curve until the other one kind of takes over. Okay. So our first one, that's just x cubed over 3 from 0 to 1. And the next one is 2x minus x squared over 2 from 1 to 2. And I'm sorry, we're going to add those two together. It's the first area plus the second area. So we're going to get 1/3 minus 0. Now, this time our boundaries are 2 and 1. So that's going to be 4 minus 2. Put in parentheses the subtraction. That would be 2 minus 1. So that is our setup. And then once we add that all up, let's kind of put things together here. So all the whole numbers I see here, 4 minus 2 is going to become 0. So it really just ends up becoming 1/3 plus, because this negative would distribute 1/3 plus 1/2. And if we get a common denominator 6, that's 2/6 plus 3/6, or 5/6 square units. So that is our area that is defined. They have defined that region for us, and we just kind of have to interpret. If it hits the x-axis perfectly, then it is just the integral of that curve that is defining that area up above. So there is example 6.4.